My talk is a kind of logical follow-up of Douglas' presentation. I will probably show you fewer examples and results because I would like to introduce you to some concept of multivariate statistics for multivariate bias correction or bias adjustment. Okay. Okay. So the basic motivations and current limitations of bias adjustment have been well stated by Douglas, so I'll be quick on that. If you look at a single grid cell, for example, you're interested in temperature and you compare the observations, the distribution, statistical distribution of this variable to the simulations provided by RCM or GCM, you will see that the distribution do not fit. Okay, they are different, and you want to adjust those. This can be to drive impact models. This can be to compare climate models. This can be to conduct many different analyses on climate processes that you hope will be more realistic after your bias adjustment. So most of the widely used bias adjustment method, as Douglas has mentioned, are basically derived from the quantile mapping. To remove that, I don't know. So okay. And this quantile mapping is quite useful and quite easy to understand. This is based on the quantile plot interpretation. So when you plot your two CDF, the cumulative distribution functions, so that the probability of being lower than a given value. For example, the green is the CDF of the observations. The blue is from the simulations. When you have a new value of coming from your model, xg, okay, you just have to look at the probability of this value within this modeled CDF, and you take the same probability value and you get back to the observed value for this CDF. Okay, so the reference CDF will give you the quantiles associated to the same probability value. So that's very fast, very easy to implement, and this is why, of course, this has been used a lot. So there's many problems in that approach. Douglas has clarified many of them. And one of them is that it can generate unrealistic, unphysical situations, typically because the multidimensional properties of the simulations are not corrected. And if those multidimensional properties, spatial, intervariable, or temporal properties are biased as well in the climate simulations, then you will basically mostly preserve those biases from the climate model. So you can generate some unphysical situations based on wrong multidimensional properties. So in other words, you would like to get, for some applications, you would like to get some more spatial, realistic spatial dependencies, okay, intersite dependencies. You may want to have more intervariable dependencies or more realistic intervariable dependencies, typically correlation between different variables. And something that is more, I would say, still an open question for me, you may want to have more realistic temporal dependencies, typically autocorrelation. But we'll see that that's probably not always the case. Okay, and another aspect of those bias correction methods, bias adjustment methods, most of the existing methods, those are deterministic. In other words, you give the same entry, you will get the same output, okay? But in many cases, you like stochasticity. You like this randomness that can bring some realism to your simulations, okay? And the climate simulations do not always possess a realistic variability, so you may want to add some more stochasticity. And this is typically needed if you're interested in uncertainty of the bias correction and in uncertainty in the climate change signal. Okay, so the basic outline of my talk will focus on multivariate bias correction, bias adjustment. I will try to describe how it works, okay, and the different, let's say, the different big families that exist to do so. And I will try to show you a few results about an intercomparison that has been done last year by Bastien François to show what we gain in using MBC, multivariate bias correction, but also what we lose in using such methods. But first, I would like to come back to the difference between bias correction and statistical downscaling. So Douglas has mentioned a lot of things about those differences, and potentially some of the things that I'm going to say are quite equivalent. That's just a different way to word that, okay? So I can see at least 4 differences, technical, practical differences between bias correction and statistical downscaling. So this has been said by Douglas, but basically when you perform a bias adjustment, a bias correction, in a pure bias adjustment context, you do not want to correct the scale, the spatial resolution of your model output. So you just want to adjust the distribution, the values, but not the spatial resolution, while in a statistical downscaling context, of course, you want to somehow build some more spatial information, spatial variability within each given grid cell. So that's a major difference that, of course, can have major consequences. Okay. The second difference is a bit more conceptual, but you will see that in practice, this has consequences as well. In statistical downscaling, you are usually in what is called a perfect prognosis approach. This approach basically assumes that the large-scale information provided by the global climate models, for example, do not have biases with respect to the reference, the observations get that at the same scale that usually come from reanalysis data set. Okay, so if you do so, you can directly calibrate your downscaling model, statistical downscaling model, by relating the observed or the reference large-scale information you have at your disposal, based on reanalysis, for example, to the local scale data set you want for your calibration, based on station, for example. And if you do so, you will need to get the temporal matching between the large scale and the local scale data you want to use. So you have to do so based on reanalysis or something that is temporally consistent with your observations. So you can calibrate, you have many different methods to do so. I will not go into details here, but you can calibrate your statistical model based on reanalysis for the large scale and on observations, station data, for example, at the local scale. And once your model is fitted, you can project what the climate model will look like at a local scale simply using this information. But once more, you make the assumption that your large-scale simulations are consistent or without any biases with respect to your reanalysis. Okay. This is a bit different for the bias correction approach, which usually relies on the model output statistics context. Here, you do not assume that your large-scale simulations do not have any bias. Okay, that's typically the goal of the bias correction. You want to correct those bias. And as the climate simulations do not temporally match the observations or the reanalysis, you cannot directly fit the link between the climate model and the observations based on events, based on time series. So how do you do so? How do you relate your simulations to your observations without any raw time series? Basically, you have for example, temperature coming from a simulation of a given model. You have observed temperature, and there's no daily synchronicity. There's no temporal matching between those two, okay? And the main idea of model output statistics or bias adjustment is not to link the event of the simulations with the event of the observations, but the main goal is to link the distributions between the two data sets. So if you link distributions, you don't need any more the temporal matching between those two. You don't have any more temporal matching, okay? That's why the quantile approach has been developed, for example. The consequence of that is that when you work in a bias correction context, you have the exact same predictor as the predictant of interest. You have the exact same variable at the given by the simulations at the variable of interest you want to provide at the end. While it can be completely different with statistical downscaling, for example, for a given variable such as precipitation, usually you can employ quite a lot of different large-scale predictors to do so, okay? So in a multivariate context, in a bivariate context, for example, if you're interested in generating bias adjusting temperature and precipitation together, including their dependencies, you start from the simulated couple temperature and precipitation, from the joint distribution of temperature and precipitation. And finally, the consequence of that is that for a given statistical downscaling model, as is it fit on reanalysis to link the observations? If you have n multiple climate model, okay, you can use the same statistical downscaling model that is fit only once. But if you have n climate models, in a bias correction context, you will have to fit to calibrate n bias correction models. You have one correction per climate model, while you have only one statistical downscaling model for all n climate models. And so that's a big difference. Okay, basically what I've just said is true as well for the univariate and the multivariate bias correction. So, but why do we need a multivariate bias adjustment method? Okay, so to investigate the bias in a univariate context, 1D, one-dimensional context, it's quite easy. Typically, you can look at various aspects of the time series of the distribution. This is what we'll look at here. We just compare the two PDF, the probability density functions of the two variables for one grid cell, for example. But you have many more ways to look at the biases in multivariate context. And for example, on the right-hand side here, on the A figure, you can see for some reference dataset, observational dataset, the correlation between temperature and precipitation for each grid cell. Okay, so that's the so-called observed correlation between those two variables. And if you take one climate model, here it's the IPS-LCM5 model, when you compute the same correlation, you will see that the patterns are quite different. And of course, these can have huge repercussions and consequences in many studies, including impact studies. So what we basically look at here is that this model have biases in its intervariable correlation. But of course, you can look at that in terms of spatial or temporal or cross correlations as well. Okay, so the question is basically, well, is it possible to adjust the marginal distribution, the univariate distribution and time series, but also those multidimensional properties? Okay, so before going to how performing bias adjustment in a multivariate context, I would like to get back to one basic notion of statistics. I will not define properly what is a multivariate distribution. You can find that in any statistical book or even on the web. But I would like to emphasize a way to describe this multivariate distribution. And this can be done by knowing that any multivariate distribution in n dimensions actually corresponds to n univariate distribution. Okay, let's say you have temperature and precipitation. You have two variables, so you have two marginal distributions, two PDF, basic PDF, and a rank-dependent structure allowing to link those two marginal distributions. Okay, so you have in green, for example, let's say it's temperature at a given grid cell. In blue, it's temperature at another grid cell, and you can see the joint distribution here. And those two marginal distributions are linked through what we call the copula function. The copula function, so here it's the only equation I will put in my presentation. Hope it will not be too painful for you, but basically you have those two distributions. And what's saying this theorem, the Sklar theorem, is that when you have a joint distribution H, which is the distribution allowing to characterize the probability of both events simultaneously, both variables simultaneously, you can simply write this distribution as a function C applied to the two marginal distribution. Okay, so this function C is called copula function. It couples the two marginals to provide the joint distribution. Okay, I will not go into details here. The interesting point is that you have many various copula functions, an infinity in practice, of course. And when you bias correct the marginal distribution, for example, based on the quantile mapping application, you only correct the marginal. In other words, you do not correct the copula function. The copula function that characterizes the dependence or the correlation between the two marginals will basically be preserved by the univariate bias correction. In other words, this will correspond to the copula function, the dependence given by the simulations, by the climate models itself. Okay. So that's, well, that's what I've just said here. In other words, when you perform a univariate bias correction, you do not change the dependence between the variables. Okay, you preserve the dependence given by the model. In other words, if you want to bias correct in a multivariate context your simulations, you will have to correct this dependence. In other words, you will have to correct the copula function itself. Okay, so this is exactly the idea used by the first family to perform MBC. The first family, hereafter I will refer to it as a marginal and dependence correction, because actually it separates the correction of the univariate properties, typically with a quantile mapping approach or whatever your favorite bias correction method. So it separates the correction of this 1D time series from the correction of the dependent structure, the correction of the copula function, if you will. And a third step consists in joining those two corrections to provide the multivariate bias corrected time series. Okay. So once more, I will not go into the details of the different methods to do so, because you have plenty of methods here. And these are basically the some recent works on that. But parallelly, you have another approach. You have another family to tackle this MBC question. And this approach does not separate marginal and dependence correction and try to correct those two altogether. Okay, marginal properties and dependent structure. Actually, I know only those two papers working on that. The basic idea here in that context is usually to work on the optimal transport theory that allows to, let's say, transport the multivariate distribution, okay, to another multivariate distribution. So in this simple example, that was simply the two Gaussian, two bivariate Gaussians that was modified. And to do so, usually you have to minimize a cost function to transform one into the other, which is based on the Wasserstein distance, which is quite famous in optimal transport theory. The very interesting point with that optimal transport approach is that it really is a generalization of the quantile mapping approach, in the sense that if you look at the equations, if you apply this typical transformation on a univariate case, you will get the exact same results and the exact same equations as the one provided by the quantile mapping approach. So in many papers, including some of those, you can see the word generalization of a quantile mapping approach. It's not true. This is the only approach that is a real generalization of the quantile mapping approach in a multivariate context. And the final family I want to mention today about multivariate bias correction is so-called the successive conditional correction. So the sketch is really simple. You have a first variable, let's say temperature, that you start to correct. So you have a generated time series corrected for this temperature. Then for another temperature at another location or another variable like wind or precipitation, you will correct this variable, but conditionally on the corrected first variable. And so on. The third variable will be corrected conditionally on the corrected variables 2 and 1, and so on and so forth. Okay. So this is quite intuitive, I think, and you have a few papers that worked in that direction over the last few years. But in practice, you have two very strong issues. And the first one is that the order of the conditioning you perform really matters. If you, in some cases, if you bias correct temperature first and precipitation conditionally on temperature, you will not get the same result at all as if you corrected precipitation first and temperature conditionally on precipitation. And the results are quite difficult to interpret because they can be highly variable depending on the order, the conditioning order you choose. The second issue for that, which is quite big in practice actually, is that even in dimension 2, you will need a lot of data to get something relevant for your conditioning. If you condition, that means that you will have to estimate a conditional distribution, okay? And you will need a lot of data to estimate rigorously your conditional distribution. This means that even in dimension 3, most of the time you will never have enough data to get something rigorous to estimate your jointly conditioned distribution. So in practice, what I recommend, if you have more than 2 dimensions, do not use that. You will never be able to get some robust information from that. Okay, and based on those considerations, we have performed with a PhD student of mine, Bastien François, an intercomparison of some multivariate bias corrections, and to try to understand what are their advantages. But most of the question was also, what do we lose when we use some specific NBC methods? So in that context, Bastien has used three different multivariate bias correction coming from the marginal and dependence family. In other words, trying to separate univariate bias correction for the marginal distribution and correction of the dependent structure, plus one all-in-ones method trying to correct everything at once, marginals and dependencies. So once more, I won't go into details here, but in a nutshell, the first method called MREC has been developed by Andras Bardossier and Joe Pegram a few years ago, almost 10 years ago. The interesting point is that they are based on a Gaussian assumption of the dependence of the time series you're interested in. In other words, every dependence in this approach is based on a correlation matrix. And what they try to do here is try to recorrelate properly the correlation matrix. Okay. So this is a strong assumption, actually, this Gaussian hypothesis. Because in practice, of course, for many variables, you won't have this Gaussian hypothesis. The second method, developed by Alex Cannon a few years ago, is called MBCN. So it's a bit tricky to explain this method, but it's based on an iterative process. And at every iteration, you will correct, in a univariate case, your data set. Okay. And before correcting in a univariate way your different data set, you have to transform your whole data set in a way that you remove the dependent structure. Basically, you try to make the data set independent. You correct, then you go back to the real world and you iterate this procedure. So basically, that corresponds to local Gaussian assumption, because when you try to make them independent by this matrix transformation, you assume some kind of Gaussianity, but because you perform this in an iterative way, you do not have any Gaussian assumption at the end. Okay, so that's a bit tricky, that's a bit technical, but that's an iterative process, partially stochastic process, because the independence transformation is made based on random matrices. But at the end, you are able asymptotically to get the correct dependence structure. The third method I wanted to emphasize here is the R2D2 method that I have developed with some colleagues a few years ago as well, and which is based on conditional resampling of the multivariate ranks to adjust the multivariate dependencies. In other words, to adjust the copula functions. And the weakness, although we can wonder if it's really a weakness, it's that it's based on the assumption of the stationarity of the dependence. That means that the dependence you will provide after your MBC, R2D2 MBC, comes from your reference observations. Okay, so you basically will try to mimic the copula function of your references. But the question is, do we really have a significant evolution in the copula function in a climate change context? So that's another question that we can discuss later. The interesting point with the resampling method is that it can work in very high dimensional space. You can, I tested it with more than 10,000 dimensions, and it works quite easily and efficiently. The quality of the results is another question, but in practice, it can work quite easily in very high dimension. And finally, the last method, as I mentioned, is based on the all-in-ones family. It's called DOTC, developed by Johan Robin a few years ago, recently, based on optimal transport theory, and there's no stationary assumption here. So meaning that the dependencies can evolve in time and trying to respect the evolution of the dependencies within the climate simulations. Okay, and in addition, of course, we have one univariate bias correction method that is a variant of a quantile mapping approach that is called CDFT here. Okay, so those different methods have been compared in terms of temperature and precipitation. As a reference, we had the WFDEI reanalysis dataset. And the model to be corrected was taken from the IPSL CM5 simulation that has been regraded to the reference spatial resolution. Actually, we performed this analysis as well for other climate models, but the results are quite equivalent. The intercomparison has been performed over France, which for this spatial resolution correspond to 321 grid cell, and over the 1979 to 2016 time period. Here I will only show the results for winter, but of course we have more for the other seasons. And the evaluation is a classical cross-validation, so of course, this can suffer from the same problems as Douglas has mentioned in the previous talk. Okay, multivariate bias correction basically can be applied in different configurations, at least 3 different configurations. In its simplest form for our dataset, the basic configuration is a 2D configuration, 2-dimensional configuration, where basically for each grid cell, you want to correct temperature, precipitation, and of course, the dependence between temperature and precipitation. So you only have the 2 variables. So as we had more than 300 grid cells, we have more than 300 multivariate bias correction to run, okay? Of 2-dimensional each. So in that context, your correction is performed locally. So you do not correct explicitly, at least, the spatial dependence between the different grid cells. So the other configuration that can be used, of course, focus on the spatial properties. Here, for temperature, for example, the goal is to correct all temperature grid cell time series all together. Okay, so what you want to correct is the intersite dependencies between the 300 grid cells. So you can do so for temperature and separately for precipitation. This means that we have 2 MBC method to apply, one for temperature, one for precipitation, and each method has more than 300 dimensions. And obviously, the last configuration is what we call the full version, where we try to correct all together the intersite dependencies and the intervariable dependencies. In other words, we have only 1 MBC to run, but based on 642 dimensions. Okay, and here I will only show the results for this full configuration. You can retrieve the other results in the paper by Bastien. Okay, first, Bastien has performed an evaluation of the intervariable properties. So this means in terms of correlation between daily temperature and precipitation. Here you can see the biases, all that figures only show differences of the model with respect to the reference correlation between temperature and precipitation. So you can see some very highly negative biases of correlation for the IPSL model. What's interesting here is that typically the quantile mapping approach will preserve those biases. It's not made to correct these correlations. So the biases we see in the climate model are also retrieved in the univariate bias correction. And when you look at the results for the multivariate bias correction, typically you see that R2D2 by the resampling approach is quite well, based, of course, on a stationary hypothesis, but that can come from the fact that between the calibration and the projection period, we don't have any significant change in the copula function. So basically, R2D2 is doing the job in that context. And DOTC and MBCN are, well, not so bad. They improve the IPSL and quantile mapping approach. But when you look at the ENES-RI method based on the Gaussian assumption, typically it explodes. It is not able to provide any robust information about the intervariable correlations. Keep in mind that those results are from the full version. In other words, these can be quite tricky for some methods to adjust the 600-dimensional problem, okay? And typically, the more we increase the number of dimensions, the more we can see deterioration for some methods, and this is typically the case for the ENES-RI method. Okay. We also looked at the spatial properties. Okay, spatial properties here was considered in terms of correlations of the same variable, temperature with temperature and precipitation with precipitation. So correlations between different grid cells, and this has been plotted here as a correlation in function of the distance of the grid cell. Okay, so this is for a smaller region because it does not really make sense to look at it in a continental scale or even at a country scale for France. And basically, we see that many methods, so this is for R2D2, this is for DOTC, this is ENES-RI, even ENES-RI for temperature at least, they do the job. Okay, even in high dimension, they do the job. So for temperature, I would say that the method with the Gaussian hypothesis does the job because temperature is quite Gaussian. So the dependence only simplified by in terms of correlations gives you the sufficient information to characterize these spatial properties. Of course, this is not the case when you look at precipitation, which is not Gaussian anymore. And interestingly as well, these spatial properties, at least in the full configuration approach, is not well reproduced well. That was expected by the univariate method. But for some other method, it was more surprising. And typically for the MBCN method, where we see that at the very beginning, in other words, for very short distances in a high dimensional context, the correlation completely drops, while in the dataset this is not the case. So this was a bit surprising, but it was quite robust for all models we tested here. And finally, for the comparison here, we looked at the temporal properties. You have to keep in mind, that's a very important message to get, when you apply any multivariate bias adjustment method, you will necessarily modify the temporal properties of your simulations. By improving whatever the spatial correlation or the intervariable correlation, you will have to change somehow the chronology of your events. In other words, when you only work with spatial or intervariable method, you do not constrain on the temporal properties, and so you can get some very weird results, unexpected behaviors of your corrected simulations. So here, in terms of temporal properties, we looked at the biases of the order 1 autocorrelation for precipitation. Okay, so that's the correlation of precipitation with itself, but only lagged by 1 day. So this is the results for IPSL. This is the results for CDFT. You can see that for CDFT, in terms of precipitation, there is already a change, okay, which is not the case for temperature. This mostly come from the dry days, actually, that are changed from the IPSL to the quantile mapping results. And when you look at the other method, the multivariate bias correction methods, you can see that none of them are really able to correct those temporal properties. This is not their goal. They were not designed to correct the temporal autocorrelation, but they were not constrained not to destroy them. So we have to be very careful in using MBC method not designed for temporal properties, because you can have some very weird results. Okay, how much time do I have left?
Well, if you could finish in 5 minutes, that would be nice.
Yeah, I should be able to do so.
Okay.
Let's try. Okay. So recently, as a conclusion, you have understood that there were a few multivariate bias corrections that have been developed, most of them in the last 5 years, and you have more and more coming up in the literature. But you have to ask yourself, when you use such a method, which configuration, which configuration is important for me? What kind of multivariate properties I really want to correct? And this choice can degrade the other properties. So we have to be careful, for example, in using a two-dimensional configuration with this, which is the simplest one. You can completely destroy the spatial properties. So be careful in that. The other point is that the temporal properties so far are not much accounted for in the developed method. So recently you have some method that try to tackle this question. You have, of course, many more than that. But this is an important question, as in many impact studies, this temporality, the chronology of the event of when they arrive, can be quite important features. Okay, I did not talk much about non-stationarity, but basically some methods try to mimic the evolution of the dependencies seen in the climate simulation. Some others are based on stationarity assumptions of the copula function of the reference. Basically, they do the job, they do what they are designed for. But this is an important question as well when you apply such methods. And something quite important, I've seen in some papers, people using bias correction in the multivariate context, but in very high dimensions. And you can create some very large instability if you don't pay attention to that and to the robustness of the results. So in other words, when you apply MBC, you should not use them blindly. That's important to investigate what they're able to do in your specific context and what they could degrade for the other properties that could still be important for your application. Okay, this is just to tell you that in paper by Bastien François, there was a table trying to summarize those different aspects. And compared to the univariate bias correction, where typically you see that such quantile mapping approach are not able to correct the intervariable spatial and temporal properties. And depending on your application, you may be interested in one of those methods, but not the other, so be careful. Okay, maybe I will skip that quite quickly, but as you know, machine learning or deep learning is everywhere today. And of course, it is also present in statistical downscaling and multivariate bias correction. And I just want to highlight one method by Bastien François recently, who worked with generative adversarial network. And basically, the idea is the following. This comes from the computer vision methods, where, for example, you have many images of zebras, but you want to generate images of horses. So you train your methods to transform those images to horses. And when you have a new image of zebra, you can correct those images into the appropriate one you want. So in practice, you have a neural network starting from noise and trying to generate some cats, for example. It's crazy the number of examples you can find on the web based on animals and specifically on cats, actually. Anyway, the interesting point here is that this cat does not exist in reality. This was completely generated by the generative adversarial network. Of course, in climate context, you don't want to generate cat from noise, but the idea is the same based on neural networks. You want to start from a bunch of images of fields generated by a climate model, and you want to transform them in a way that they look more realistic as coming from reference. Okay, I won't go into the details, but you basically have two different neural networks trying to fight each other. One is trying to generate images, and the other one, the discriminator, is trying to not to be fooled by generator and saying, well, this one is not a real one, so improve it, please. Okay, just three last comments. That's my last slide about some open questions and perspectives for multivariate bias corrections. First of all, MBCs are made to improve, of course, the realism of the climate simulations in terms of various dependencies. One interesting question nowadays is how much does this improvement propagate to impacts, and for example, in terms of compound event? That would be very interesting because compound events are based on simultaneous, for example, that's not the only definition, but simultaneous appearance of climate situations. So if you improve those dependence between those events, you can expect to improve those compound events. But for me, that's still an open question. Some studies say, yes, we improve compound event. But I have to say that from my experience, it's not that clear. The important other point I want to highlight here is that correlation is not the causality. Okay, if you correct the correlation, if you adjust the correlation, you do not correct the reason for which you had a bias in correlation previously. That's strongly related to what Douglas mentioned in his talk. You can have good correction for bad reasons. So in a climate change context, that can have huge repercussions if your reasons are bad. In other words, that's typically what Douglas has said. Can I really adjust my climate model for my typical application? That's a question you should ask yourself. And of course, you have different assumptions about non-stationarity of the multivariate dependencies. And an open question for me is, should we account for changes in dependencies? When you look at ensembles of climate simulations, you can have such a high variability in terms of dependencies and such a high variability in terms of changes of dependencies that you can really wonder if you want to account for changes in dependencies in the climate simulations, or if you just want to stick to your reference for that. In other words, before applying any univariate or even multivariate biased adjustment, you may want to ask yourself, how much do I trust my model? Is it applicable for the application I have in mind? And how much and what do I want to correct from my climate model? Okay, I'm going to stop here and I'll be happy to hear your questions.